Earth, our home. It feels so utterly solid, doesn't it? Firm ground beneath our feet, mountains rising majestically, coastlines carved seemingly forever.
It really does. But deep down, far beneath the surface,
Mm.
well, our planet is a place of immense energy.
And constant, sometimes really violent change, forces we can barely imagine are at work, building, shifting.
Uh-huh. And occasionally unleashing power that reminds us, what's truly shaping this world.
Today, we are plunging into that hidden realm with a deep dive into two of the most dramatic expressions of Earth's internal dynamics, volcanism and earthquakes.
And crucially, we're going to explore the incredible and varied landforms these processes create.
Right. Our guide for this deep dive comes from a specific source, a compelling chapter from a geography textbook focused intently on these very phenomena.
So we're really digging into what this particular text emphasizes.
Exactly. Think of this deep dive as unlocking the essential knowledge nuggets, the core insights that this particular text wants you to grasp about volcanic and seismic activity. What does this source tell us is fundamentally important to understand about these powerful forces and the landscapes they forge?
It's truly fascinating to consider how these deep internal processes profoundly sculpt the Earth's outer skin, the material that fuels this. The molten rock, liquid, and gases originating from vast reservoirs far below the surface.
The magma.
Magma, exactly. What we collectively call magma finds its way upwards, creating landforms that are utterly unique to volcanic activity.
And right away, this source makes a really crucial distinction, dividing these landforms based on where that magma finally stops and solidifies. You have what are called intrusive landforms. This is where the magma pushes its way into the existing rock layers within the Earth's crust, but never actually makes it all the way to the surface.
Right, it cools and hardens while still buried. The source notes these can be formed by both plutonic, meaning deep, and volcanic, sort of shallower activity related to that upward movement.
Okay. Then, on the other side, you have extrusive landforms. This is perhaps what first comes to mind for many of us.
Yeah, the classic volcano stuff.
Right, where the magma does break through the surface and solidifies as lava. These are formed purely by volcanic activity reaching the light of day.
That distinction is key because it sets the stage for a whole range of different structures. When we look at those intrusive forms, the source details several types, primarily classified by how that molten magma is injected into the crust.
And where it solidifies relative to the rocks already there.
Exactly. Let's start with maybe the most straightforward ones described. Sills and dikes. A sill is created when magma intrudes horizontally.
Okay, sideways.
Yeah. Imagine rock layers stacked up like pancakes. A sill is when magma squeezes between those layers, spreading out horizontally along the bedding planes of sedimentary strata.
So you wouldn't see it right away.
No, the source explains that you don't see these until the overlying rock is worn away by erosion, or denudation, as the text puts it.
Ah, okay.
When exposed, they can look like sheets of solidified lava spread across the landscape. If the sill rock is harder and more resistant to erosion than the surrounding layers.
It could stand out.
Precisely. It can even form a prominent escarpment, a steep slope or cliff face. The Great Wind Sill in northern England is given as a classic example in the source of famous feature revealed this way.
Got it. So sills go sideways between layers. What about dikes?
Now, contrast that with a dike. If a sill goes horizontally, a dike goes vertically or very nearly vertically.
Okay, straight up and down, more or less.
Right. Magma cuts across the existing rock layers, like a wall or a blade. Again, these are often only seen after erosion removes the surrounding rock.
And if the dike is tougher rock?
It's left standing as a distinct, often narrow ridge. The source provides several compelling examples of these. The Cleveland Dyke of Yorkshire in England, but also hundreds of them slicing through the landscape in the Isles of Mull and Arran in Scotland.
Wow, hundreds.
Yeah. It even mentions a very large resistant dike near Kuala Lumpur, Malaysia, made of quartzite, which forms a significant ridge there. So sills follow the layers sideways, dikes cut across them vertically.
That simple difference in direction, horizontal versus vertical intrusion, leads to such distinct features once they're exposed. It's a reminder of how the path of the magma matters, even deep underground.
Absolutely. And the scale of these intrusive forms can vary dramatically. Beyond sills and dikes, the source describes larger and more complex bodies of intrusive rock.
Bigger stuff.
Much bigger. Take Laccolus. The text describes these as a large blister or an igneous mound.
A blister, okay.
Yeah, the magma is fed by a pipe-like conduit from below, similar to a volcano's vent, but instead of erupting, it spreads out laterally between rock layers near the surface. However, the magma is viscous, and under pressure.
So it doesn't just flow flat like a sill.
Exactly. Instead of spreading thinly like a sill, it pushes the overlying strata upwards, creating a dome-shaped upper surface with a level base. Think of pushing a balloon under a rug. It creates a bulge upwards.
Okay, I can picture that.
The laccoliths of the Henry Mountains in Utah in the USA are cited as a prime illustration of this process.
Right. What else?
A lopelithith is another distinct form, described as a saucer-shaped intrusion. It forms a shallow basin shape, often very large.
Saucer shape, so it sags in the middle.
Kinda, yeah. The Bushveld lopelith in the Transvaal, South Africa is highlighted as a significant example of this type of broad, dish-like intrusion.
Okay. And faccoliths. That sounds complicated.
It's specific. These are lens-shaped masses of igneous rock. The source specifies that they uniquely occupy the crest of an anticline, which is an upward fold in rock layers, kind of like an arch.
Right, the top of a fold.
Or the bottom of the syncline, which is a downward fold, like a trough.
The bottom of the dip.
Exactly. Like laccoliths, they are fed by a conduit from beneath and take their shape from the existing geological structure they intrude into. Corndon Hill in Shropshire, England, is mentioned as an example where this lens shape sits within folded rock.
Interesting. It fits into the curves.
Precisely. And finally, the source calls batholiths the most spectacular of the intrusive landforms.
With the grand finale.
Pretty much. These are absolutely colossal masses of igneous rocks, typically granite. Unlike the others, which might take specific shapes relative to strata, batholiths are huge, irregular bodies.
So just massive blobs of cooled magma.
Essentially, yeah. They solidify deep within the crust and are only exposed after immense amounts of overlying rock are removed by erosion over vast geological timescales. When they are finally revealed, they form massive, resistant upland regions and even mountain ranges.
Wow. So the core of mountains can be these things.
Often, yes. The source gives striking examples. The Wicklow Mountains of Ireland, the uplands of Brittany and France, and the main range of West Malaysia.
Okay.
The text describes the belief that batholiths are vast masses rising towards the surface, coming into contact with the surrounding country rocks and solidifying to form incredibly extensive areas, sometimes stretching for hundreds of miles.
Hundreds of miles. Underground.
Hundreds of miles. It's hard to even picture that scale of rock formation happening underground.
It truly puts the power and depth of these processes into perspective, doesn't it? From thin sheets squeezing between layers or walls cutting across them, to these absolutely enormous subterranean rock bodies that become the cores of mountain ranges once the surface is stripped away.
It really does. These are forces working on a scale that humbles us.
Absolutely.
And while those intrusive forms are hidden until erosion reveals them, the exclusive forms are the ones that break through the surface, often dramatically. This brings us to the very origin of volcanoes and the different types of molten material, or lava, they erupt.
Let's talk volcanoes.
You know, it's interesting to start with the historical perspective, as the source does. The ancient Greeks attributed volcanic eruptions to the forge of their god Hephaestus, the god of metalworking and fire, often associated with underground realms.
Right, the god of the underworld, basically.
Sort of, yeah. The Romans called him Vulcan, which of course gives us the modern word volcano. It highlights a long human understanding that these fiery mountains are connected to powerful, deep-seated forces.
Makes sense. What's the modern view?
Our modern geological understanding, as the source lays out, sees volcanic eruptions as a fundamental way for the Earth to release pressure built up from that molten rock, the magma, accumulating within the crust or upper mantle.
So it's like a pressure release valve for the planet.
In a way, yes. Geologists and volcanologists see a strong correlation between where volcanoes occur and areas of crustal instability, places where the Earth's crust is weakened by deep faulting or intense mountain folding.
So where the crust is already broken or stressed?
Exactly. It's where the rock is already compromised, that magma can most easily find a path to the surface.
And where does all that heat come from to melt rock in the first place?
That comes from within the Earth. The temperature increases steadily with depth. The source provides an average rate, about 1 degree ev for every 65 feet of descent.
Wow, that adds up quickly.
It really does. When you extrapolate that over miles and miles down, the interior of the Earth is incredibly hot, hot enough to be in a semi-molten state in places.
Okay. So magma isn't just melted rock, though. The source mentioned gases.
Ah, yes. What's crucial to understand about the magma itself, beyond just being melted rock, is that it's heavily loaded with dissolved gases. The source lists carbon dioxide, sulfurated hydrogen, nitrogen, chlorine, and other volatile substances.
Volatile, meaning? explosive.
They contribute significantly to that, yes.
Yeah.
These gases are absolutely critical because they increase the mobility of the lava once it reaches the surface. And perhaps more significantly, they are the primary drivers of explosive eruptions.
How so?
Imagine shaking a soda bottle. The dissolved gas builds pressure. When a volcano's vent opens, that pressure is released, and the expanding gases propel the molten rock and other material outwards with tremendous force.
So the gases trapped within the magma are like the hidden engine that powers the eruption, determining not just how easily the lava flows, but also how violently it explodes.
That's a great way to put it. And when that magma finally does reach the surface and becomes lava, the source tells us its composition fundamentally dictates its behavior and the kind of landform it builds. There are two main types it describes: basic and acid.
Okay. Basic versus acid lava. What's the difference?
Yes, this is a really key distinction that helps us understand the variety of volcanic landscapes we see. Basic lavas, often called basaltic lavas, are the hottest, around 1,000 degrees Cedar or 1,830 degrees Fahrenheit. Extremely hot. And critically, they're also highly fluid. They flow very easily. Their composition is dark-colored, rich in iron and magnesium, but relatively poor in silica.
So hot, runny, dark lava. How does it erupt?
Because they are so hot and so fluid, basic lavas tend to erupt relatively quietly. They pour out rather than explode violently.
More of a flow than a bang.
Exactly. And their high fluidity means they flow rapidly, sometimes moving at speeds the source mentions of 10 to 30 miles per hour.
That's fast for lava.
It is. Think of water flowing downhill compared to thick syrup. This allows them to spread out over vast distances before they cool and solidify into thin sheets.
So what kind of landforms do they make?
The landforms resulting from these flows are typically very broad and relatively flat. They form extensive lava plains and vast basalt plateaus.
Like huge sheets of cooled lava.
Precisely. The Deccan Plateau of India, the Snake River Plain in the USA, and the basalt platforms of Iceland are given as classic examples. They also build a specific type of volcano called a shield or dome volcano. Because the lava spreads out so easily, these volcanoes have very gentle slopes, a wide base, and a flattened summit, resembling an overturned warrior shield.
Ah, that makes sense. Like the Hawaiian volcanoes?
Exactly. Mauna Loa and Kilauea in Hawaii are prime examples of these gentle flowing shield volcanoes.
Got it. So that's basic lava. What about acid lava?
Acid lavas, on the other hand, are quite different. They are cooler than basic lavas, and more importantly, they are highly viscous. They have very low fluidity. They are thick and sticky.
Cooler and stickier. What's in them?
Their composition has a high percentage of silica. That's the key difference chemically.
Okay, so how does this sticky lava behave?
Because they are so viscous, they flow very slowly. They don't travel far from the vent before solidifying.
Right, they pile up.
They do. As they cool and pile up around the eruption point, they build a resistant cone. This resistant structure tends to obstruct subsequent flows, leading to pressure building up beneath the surface.
Ah, so the stickiness traps the gases.
Exactly. This is why eruptions of acid lava are often much more explosive than those basic lava. The gases trapped in the thick magma escape violently when the pressure is finally released.
That makes sense. What kind of shapes do they make?
The landforms they create reflect this viscosity and explosive potential. They typically form steep-sided cones or rounded, bulbous lava domes, like Mount Pelée in Martinique.
Steeper sides because the lava doesn't flow far.
Right. Sometimes if the lava is extremely viscous and solidifies right in the vent, it can form a solid plug or even a vertical spine of rock that rises from the crater.
A spine, like a spike.
Yeah. The source mentions the spine of Mount Pelée, which rose nearly 1,000 feet high months after the devastating eruption, as a famous example. While erosion might wear away the cone later, such a resistant plug could remain.
Wow. Any other features from this thick lava?
This type of less fluid flow can also create other features, like lava tongues, short, thick flows that don't get far. Lava tunnels and bridges formed when the surface of a flow hardens, but the interior continues to flow. And even dammed lakes created when a lava flow blocks a river valley.
Wow. So the difference between a broad, gently sloping shield volcano in Hawaii and a steep, explosive cone like Mount Pelée really comes down to the chemistry and temperature of the magma driving it, whether it's fluid like hot oil or thick and sticky like peanut butter.
That's a perfect analogy. It really captures the essence of it.
That's a powerful connection. Now, speaking of the structures themselves, the source categorizes volcanoes based on their level of activity. It gives us 3 classifications: active, dormant, and extinct.
Right. These classifications help us talk about the potential risk or current state of a volcano. Active volcanoes are those that erupt frequently or have erupted relatively recently.
And might go again soon.
Exactly. They show ongoing signs, like gas emissions or ground swelling, indicating that future eruptions are likely.
Okay, what about dormant?
Dormant volcanoes are those that haven't erupted in living memory or in very recent times, but they have erupted in historical periods.
So they could erupt again.
Absolutely.
Sure.
Critically, they still retain the characteristic structure of a volcano, meaning the plumbing system beneath is likely still intact, and they absolutely retain the potential to erupt again.
Any famous examples?
Yes, the source gives some famous examples of volcanoes that were considered dormant before they reawakened, underscoring the uncertainty. Mount Fuji in Japan, Popocatépetl in Mexico, Chimborazo in Ecuador,
And Vesuvius? Krakatoa?
and perhaps most famously, yes, Vesuvius in Italy and Krakatoa in Indonesia. Both were thought dormant before their big eruptions.
Wow. Okay, so dormant is definitely not safe. What's extinct then?
Extinct volcanoes, on the other hand, are thought to be permanently inactive. They haven't erupted in historical times, and often their structure has been significantly eroded, sometimes to the point where the volcanic origin isn't immediately obvious.
Suggesting the magma source is gone or blocked?
Pretty much, yes. The source has solidified, or the pathway has been permanently sealed off.
So dormant is really just a sleeping giant, while extinct is a giant whose time has truly passed. That's a critical difference for anyone living near one.
A very critical difference.
Let's circle back to those extrusive landforms themselves, the visible structures built by eruptions. The source dives deeper into the main types of volcanic cones, which are shaped by the nature and mix of erupted materials.
Indeed. We've touched on shield volcanoes, built by that fluid basic lava.
And lava domes from the sticky acid lava.
Right. But the source highlights a couple of other very common and important types.
Okay, what are they?
There are cinder cones. These are built up primarily from fragmented material ejected during an eruption, things like cinders, ash, volcanic bombs, lapilli, and scoria.
So basically bits of rock blasted out.
Exactly. These fragmental rocks are collectively called pyroclasts. Think of them as rocky debris blasted out. Cinder cones tend to have steep sides because the loose, fragmented material piles up at a high angle.
Makes sense, like a pile of gravel.
Yeah, but they're generally relatively small compared to other volcano types. The source notes they're often found associated with larger composite cones, sometimes erupting from vents on their flanks.
Okay, small and steep, made of fragments. What's the other main type?
And then you have the composite cones, also known as stratovolcanoes. The source describes these as the highest and most common type of large volcano globally.
The classic pointy volcano shape.
That's usually them, yes. They're built up from alternating layers, layer upon layer of lava flows. Both basic and acid flows contribute, and layers of those other volcanic materials like ash, cinders, and bombs.
So layers of lava and layers of fragments.
Exactly. This layering of strong lava flows alternating with looser pyroclastic layers creates a very strong structure that can build tall peaks. The material typically erupts from a main conduit at the summit.
But not always.
Right. As the cone grows, subsidiary dikes or pipes can carry magma outwards, erupting on the flanks and building smaller cones there, called parasitic or adventive cones.
Little side volcanoes.
Kind of. Mount Etna in Italy is a classic example, famous not just for its main summit crater, but for having literally hundreds of these smaller parasitic cones on its slopes.
Hundreds. Wow.
Yeah. The source lists many iconic volcanoes that are composite cones. Vesuvius, Mount Fujiyama in Japan, Popocatépetl in Mexico, Chimborazo in Ecuador, Etna, and Stromboli in Italy. It even mentions Stromboli is called the lighthouse of the Mediterranean due to its frequent visible activity.
Okay, so composite cones are the big layered ones. That covers the main types.
So you have the gentle sprawling shield, the steep sticky dome, the small steep cinder pile, and the tall layered composite cone. Each tells a story about the material and style of eruption that built it.
Makes sense. What about features after an eruption? Craters and things.
Right. Beyond the cones themselves, the source also discusses larger depressions associated with volcanoes, formed either during or after eruptions. Craters are the most common. They are the bowl-shaped depressions typically found at the summit of a volcano where the main vent is located and from which volcanic material erupts.
The hole at the top.
Basically, yes. Calderas are much larger features. They are vast depressions, often many miles across, sometimes encompassing the remnants of a former, much larger volcano.
Much bigger than a crater. How do they form?
Calderas form not by material being erupted outwards, but by the volcano collapsing inwards.
The mountain falls in on itself.
Exactly. This can happen after an incredibly large eruption that empties the magma chamber beneath the volcano, removing the underlying support and causing the ground above to subside. It can also happen simply due to the weight of a massive cone built on an unstable base.
And these can fill with water.
Yes, these enormous collapsed basins often fill with water over time, forming spectacular caldera lakes, such as Crater Lake in the USA or Lake Toba in Sumatra, Indonesia.
So craters are where stuff comes out, and calderas are where the mountain itself falls in. It's a pretty dramatic life cycle for these giant structures.
Very dramatic.
This textbook chapter also highlights the sheer power of these events by focusing on some particularly notable volcanic eruptions from history. Let's delve into 3 specific ones it details.
Okay. First, the eruption of Mount Vesuvius near Naples, Italy, in AD 79. This was a famously violent event that occurred on August 24th.
Pompeii and Herculaneum, right?
Exactly. The source describes a complex, multi-stage catastrophe. White-hot lava did flow down the flanks, but it wasn't just lava. In the midst of a thunderstorm, a highly gaseous magma escaped, not as a simple lava flow, but as a gigantic, luminous cloud of ash, gas, and rock fragments.
A cloud.
Described as having a terrifying cauliflower shape, which shot up to great heights into the atmosphere.
And the impact.
Horrific. Ash and cinders rained down relentlessly on the Roman towns of Pompeii and surrounding areas, burying them quickly. But the source emphasizes that for Herculaneum and other towns on the slopes, a rapid, devastating mud flow, or lahar, occurred.
A mud flow.
This is a mixture of volcanic ash and cinders mixed with torrential rain that happened simultaneously. This mud flow, described as being up to 50 feet thick, washed down the flows with immense speed and force, burying the entire population of towns like Herculaneum almost instantly and preserving them in that tragic moment.
Unbelievable. Okay, what's next? Krakatoa.
Next, the eruption of Mount Krakatoa in August 1883. This volcano was located on a small island in the Sunda Straits, situated between Java and Sumatra in Indonesia.
And this was huge.
The source describes this event as arguably the greatest volcanic explosion ever known to humans. The eruption column, a mixture of ash, gas, and debris, was so powerful it shot 20 to 50 miles high into the atmosphere.
Miles high.
Yeah. The explosion itself, caused by the volcano collapsing into a caldera under the sea, was of unimaginable force. It was so loud, the source says, it was heard some 3,000 miles away.
3,000 miles. Incredible.
And the fine dust blasted into the atmosphere, traveled around the entire globe, circulating for a year, causing unusually brilliant sunsets and changing sky colors worldwide.
So the main damage wasn't lava.
No. While there were some lava flows, the main destructive force here wasn't the lava. The primary catastrophic impact came from the massive tsunami the explosion generated.
Ah, the explosion triggered waves.
Huge waves. They reached up to 120 feet high in the narrow Sunda Straits, utterly devastating the coastal districts of Java and Sumatra, and drowning an estimated 36,000 people.
36,000. Devastating.
Absolutely. The shock waves from the blast were so powerful they vibrated measuring instruments across the Earth's surface. It's also geologically interesting because Krakatoa was thought to be extinct before this massive eruption.
Another dormant one waking up.
Right. And since then, a new volcano, a cinder cone named Enek Krakatoa, meaning child of Krakatoa, has grown from the submerged caldera.
Wow. Okay, the third one, Mount Pelée.
Finally, the eruption of Mount Pelée in May 1902, located on the island of Martinique in the West Indies. The source calls this the most catastrophic eruption of modern times, specifically because of a particular type of eruption called a nuée ardente.
French for glowing avalanche.
Exactly. This wasn't a slow lava flow, it was a superheated cloud of gas, ash, and volcanic debris that erupted laterally from the volcano and swept down the slopes at incredible speed and searing temperature.
Not up, but sideways.
Sideways and fast. The impact was devastatingly swift and complete. The nuée ardente obliterated the capital city of Saint-Pierre in mere minutes.
The whole city.
Wiped out. The entire population of 30,000 people was killed almost instantly by the heat and force of the cloud, with only 2 recorded survivors. Even ships anchored in the harbor were wrecked.
Unimaginable speed and heat.
Precisely. This eruption is also notable for the viscous spine of solidified lava we mentioned earlier, which rose almost 1,000 feet high from the crater in the months that followed, a testament to the sticky, acid nature of its magma.
Those accounts are chilling and powerful, highlighting the diverse ways volcanoes can kill and destroy, from burying towns in ash and mud to triggering continent-spanning explosions and tsunamis, to unleashing lightning-fast avalanches of superheated gas.
Each event a unique, terrifying display of Earth's power.
Absolutely. Shifting gears now, the source moves to the larger global picture, looking at the distribution of both volcanoes and earthquakes. It points out that these aren't random acts of geological fury. They are concentrated in very specific, clearly defined patterns across the planet.
That's a crucial insight. Volcanic activity, as the source notes, is overwhelmingly located in areas that have experienced significant crustal deformation, places that have been intensely folded or faulted due to the immense pressures within the Earth's lithosphere.
So where the crust is already stressed and broken.
That's the key. The most prominent of these patterns, highlighted by the text, is the Circum-Pacific region. This area, famously known as the Pacific Ring of Fire, encircles the Pacific Ocean basin.
The Ring of Fire, yeah. Lots of activity there.
Huge amounts. The source states that this single zone contains the greatest concentration of volcanoes on Earth, estimated to be about 2/3 of the world's volcanoes. And critically, it's also closely associated with the planet's major earthquake zones.
Volcanoes and earthquakes together.
Very closely linked. The source lists many of the volcanic hotbeds along this ring of fire, showing its vast extent. It runs along the Aleutian Islands off Alaska, down through Kamchatka, Japan, the Philippines.
Which has loads of volcanoes, right?
Yeah, the source notes there are around 400 active volcanoes there. Then through Indonesia, Java, and Sumatra particularly active, part of roughly 70 active ones in Indonesia,
Okay.
and continues into the Southwest Pacific through the New Hebrides, Tonga, and the North Island of New Zealand. Then it stretches across the Pacific to the Americas, running along the Andes Mountains of South America through Central America,
Guatemala, Costa Rica.
exactly mentioning Guatemala, Costa Rica, Nicaragua, and up along the Pacific coast of Alaska and North America. It's a near continuous belt of volcanic and seismic activity.
Wow, it really circles the whole Pacific. What about other oceans? The Atlantic.
In contrast to this intense concentration, the source notes that areas like the Atlantic coasts have comparatively few active volcanoes. Though there are exceptions mentioned, such as Ascension, St. Helena, the Cape Verde Islands, Iceland, and the Azores, many of which are island volcanoes, perhaps reflecting slightly different geological settings.
Okay. Any other major areas? Africa, Europe.
Other notable volcanic regions mentioned include areas in Africa like the iconic Mount Kilimanjaro and Mount Kenya, and the Mediterranean region, with historical and currently active volcanoes like Mount Ararat, Etna, Stromboli, and Vesuvius.
Right, Vesuvius again.
The source also points out that active volcanoes are quite rare in the vast interiors of continents across North America, Europe, and Asia.
Mostly coastal or specific zones.
Generally, yes.
Yeah.
Now, when we look at the distribution of earthquakes, the source makes it very clear. There is a strong correlation with volcanic activity. Major earthquake zones often coincide with these volcanic belts, especially the Circum-Pacific Ring of Fire.
So the maps would look similar.
Largely overlapping, yes. But it also identifies another major separate belt of earthquake activity that isn't primarily volcanic, the Mediterranean Himalayan belt.
Okay, where's that?
This zone stretches from the Mediterranean Sea eastward through the Himalayas and into parts of northwest China, marking another area of intense crustal stress and movement.
So mountains being built there cause quakes.
That's the implication, yeah. Areas of intense folding and faulting. The text notes that some areas of the Earth's crust are relatively stable and less prone to major quakes, such as the East African Rift, though, that has its own kind of activity, and others experience only minor Earth tremors, indicating that while the whole Earth is dynamic, the forces are concentrated along these defined belts.
So the map of volcanoes and the map of major earthquakes largely overlap, painting a clear picture of where the Earth's crust is most actively being pushed, pulled, and fractured.
Exactly. It's along these lines of weakness that the energy is released, whether it's flowing lava or ground-shaking tremors.
Okay. Before we dive fully into earthquakes, the source touches on a couple of related phenomena, often found in these very same geologically active thermal regions. Geysers and hot springs.
Ah, yeah, they're another surface manifestation of that heat and activity underground.
Like natural plumbing connected to the heat.
Pretty much. Geysers, as the source defines them, are fascinating fountains of hot water and superheated steam that periodically erupt from beneath the Earth. They're strongly associated with areas of recent or ongoing volcanic or intense thermal activity, where hot rock is close enough to the surface to heat groundwater.
So how do they actually work? Why do they erupt like that?
The mechanism described is quite specific and clever. Water seeps down through cracks in the rock and gets heated at depth by contact with those hot rocks. Because the water is underground, it's under pressure from the column of water above it.
Right, pressure keeps it from boiling normally.
Exactly. This pressure prevents the water from boiling at its normal surface boiling point of 100 degrees C, 212 degrees Fahr. It becomes superheated, hotter than the boiling point, but still in a liquid state due to the pressure.
Okay, super hot water trapped underground.
Right.
Then what?
Eventually, the water at the top of the column or in a constricted part of the fissure flashes to steam, perhaps because the pressure is slightly relieved or it reaches a critical temperature. When a small amount flashes to steam, it expands dramatically, pushing the water above it out of the vent.
And then that release triggers more boiling.
Precisely. This reduces the pressure on the superheated water deeper down, causing it to instantly flash to steam in a chain reaction. This rapid expansion of steam is what causes the explosive jet of hot water and steam to erupt upwards the geyser.
Oh, that makes sense. It's a chain reaction.
Yeah, the source mentions their periodic nature, like the famous Old Faithful, which erupts on a relatively predictable schedule because the underground plumbing allows this pressure building and release cycle to repeat consistently.
Amazing. So how are hot springs different? No explosion.
Right. Hot springs, on the other hand, are a simpler manifestation. They are just areas where naturally heated water rises to the surface, resulting in pools or streams of warm or hot water. They are also found in volcanic or thermal regions, heated by the same underground processes as geysers.
But the water just flows out.
Yeah, the key difference is that the water rises to the surface without being trapped in a way that allows pressure to build to the explosive point needed for a geyser eruption. It simply circulates and rises. These springs often contain dissolved minerals.
Which can make them colorful.
Exactly, which can precipitate out and create colorful deposits or unique formations. And the source notes they've historically been used for medicinal purposes or even industrial processes where a source of heat or specific minerals is needed.
Where can you find these?
The text lists areas famous for their geysers and hot springs, which unsurprisingly are found in areas with recent volcanic history. Yellowstone National Park in the USA, home to Old Faithful and countless other thermal features.
Right, Yellowstone.
The Rotorua district of New Zealand, a very geothermally active area. Iceland, a country built on volcanic activity, and also parts of Japan and Hawaii. They are direct windows into the heat happening deep beneath our feet.
So geysers are the dramatic, explosive result of trapped, superheated water, while hot springs are the gentler flow of that same underground heat. Different pathways, different expressions of the same core phenomenon.
Well put. Exactly.
And speaking of dramatic expressions, let's dedicate some time now specifically to earthquakes, the sudden, often violent shaping of the ground that is perhaps the most feared of Earth's dynamic events.
Yeah, the source makes it clear that our planet is in near constant seismic motion. The Earth is never truly free from earthquakes. There are countless, literally tens of thousands, of minor earth tremors recorded annually.
How many did it say?
The source states over 50,000 minor tremors a year. But thankfully, there are fewer major destructive earthquakes.
And what causes the big ones?
These major events are almost always caused by the sudden movement of large blocks of the Earth's crust along faults. Faults are essentially fractures or zones of weakness in the crust where movement has occurred previously or is occurring.
So the ground breaks and slips.
Pretty much. Pressure builds up as tectonic forces push or pull on these blocks, and when that pressure exceeds the strength of the rock holding them locked, the rock snaps, the blocks slip past each other, and that sudden release of energy sends seismic waves radiating outwards, causing the ground to shake.
Can volcanoes cause quakes too?
Yes, other crustal disturbances like magma moving underground or volcanic eruptions can also cause quakes, but the major destructive ones are usually those tectonic shifts along faults.
And they're so dangerous because they happen where people live.
That's a huge part of it. The source explains why major earthquakes, though fewer in number, can be so incredibly disastrous. It's not just the intensity of the shaking, though that is immense. It's that their most devastating impact is often concentrated in densely populated areas located near major fault lines.
And there are after effects too, like tsunamis.
Critically, yes. The immediate ground shaking can trigger catastrophic secondary effects. The source specifically highlights tidal waves, known as tsunamis, which are often generated by powerful earthquakes that occur beneath the ocean floor, particularly off the coast of Japan. These enormous waves can travel across entire ocean basins at high speed and then flood coastal towns with terrifying force, drowning thousands.
Just devastating. What about the shaking itself? What does it do?
The physical effects on the land and on human structures, described in the source, paint a vivid picture of chaos. Severe earthquakes cause fissures to open up in the ground, literally splitting the Earth's surface.
Cracks in the ground?
Big ones, yeah. The ground itself can undulate like waves. These are the surface waves that cause so much damage. These movements can snap infrastructure. Bridges and railway lines can be twisted and broken. Roads buckle dramatically.
Buildings must just collapse.
Often, yes. Buildings, dams, and bridges designed to withstand vertical weight are often not built to resist the side-to-side or rolling motions of an earthquake and collapse entirely. Communications can be cut as underground cables snap. On hillsides, the shaking can trigger massive landslides.
So it just shakes everything apart.
Essentially, the intense vibrations cause structures to shake apart and collapse. The intensity of this shaking is measured by instruments called seismographs, which record the ground motion.
It's not just the ground moving, it's the way that movement interacts with everything built on top of it and the secondary disasters it can unleash.
Precisely.
The source, much like with volcanoes, brings these concepts to life by detailing some major destructive historical earthquakes, showing the varied ways they inflict damage.
It does. One of the earliest and most devastating mentioned is the Great Lisbon Earthquake on November 1st, 1755.
Lisbon, Portugal. What happened there?
This quake occurred offshore from Lisbon, Portugal, on an anticlinal ridge, one of those upward folds in the ocean floor. It's estimated to have been incredibly powerful, perhaps between magnitude 8.5 and 9.
Wow, that's massive.
Huge. While the shaking caused immense damage in Lisbon, the primary catastrophic impact came from the tsunami. This earthquake generated waves up to 35 feet high that swept across the coastal districts of Lisbon and other areas,
35 feet.
drowning thousands and causing buildings that survived the initial shaking to collapse completely. It was a truly devastating event that resonated across Europe.
Unbelievable. What other examples did it give?
Tokyo. Another equally shocking disaster highlighted is the Tokyo-Yokohama earthquake on September 1st, 1923. This major quake occurred along an earthquake fault off the coast of Japan.
Another coastal quake.
Yes. The ground shaking in the densely populated twin cities of Tokyo and Yokohama caused widespread collapse of buildings. But similar to the critique of the Vesuvius event, the source emphasizes the horrific secondary effect here. Widespread fires.
Fires again. How?
Widespread fires broke out almost immediately across both cities, ignited by toppled stoves, broken gas mains, and damaged oil installations. These fires spread rapidly through the largely wooden structures, becoming unstoppable conflagrations that killed far more people than the initial shaking.
Worse than the shaking itself.
In many cases, yes. More than half the population was either killed or injured in this combined disaster.
Just tragic. Any others mentioned?
The source also lists other destructive historical earthquakes to underscore the pervasive nature of this threat in certain regions. The San Francisco earthquake of 1906, where the greater part of the city was destroyed by the resulting fire.
Fire again in San Francisco?
Yes. The Kansu, China earthquake in 1920, which was incredibly deadly, killing 200,000 people.
200,000.
The Agadir, Morocco quake in 1960, where 10,000 were killed. And a disastrous earthquake in eastern Iran in 1968 with its epicenter at Kak. Each event a stark reminder of the fragility of human structures against geological power. And circling back to distribution, the text strongly reiterates that these major earthquakes are most frequent in those same distinct global belts we discussed in relation to volcanoes, the Circum-Pacific Ring of Fire and the Mediterranean Himalayan belt.
Right, the same active zones.
These are the areas where the Earth's crust is most actively deforming, where the faults are most prone to sudden, violent movement.
It really hammers home that connection. The same underlying forces driving magma to the surface in volcanic eruptions are also building stress in the crust that's released as earthquakes. Volcanism and seismic activity are truly two sides of the same incredibly powerful coin.
Very well said.
We've traveled from the deep, hidden world of intrusive magma bodies like sills, dikes, and those huge batholiths, to the explosive drama of volcanic eruptions shaping the surface.
We've seen the incredible diversity of landforms created from the gentle slopes of a shield volcano built by runny basic lava to the towering composite cone layered with lava and ash and the vast collapsed caldera.
We've understood how the type of lava dictates the behavior of an eruption and the resulting shape, that crucial difference between fluid, basic, and sticky acid lava.
We've grasped how volcanoes are classified by their activity, active, dormant, extinct, and witnessed the devastating power unleashed in famous historical events like Vesuvius, Krakatoa, and Pele.
And we've seen how both volcanoes and earthquakes are not randomly scattered, but concentrated in distinct global patterns, most notably the Pacific Ring of Fire and that Mediterranean Himalayan belt.
Driven by the fundamental movements within the Earth's crust. We even peeked into the fascinating surface expressions of underground heat in geysers and hot springs.
This deep dive into the source material truly reveals the Earth as a dynamic, living planet, not a static stage. The forces of volcanism and seismic activity are fundamental processes, constantly at work.
Shaping and reshaping the land we inhabit over timescales that are hard for us to fully comprehend. They are a powerful reminder that the ground beneath our feet is part of a larger, incredibly energetic system.
And thinking about that energy and the clear global patterns of where it's most often released leads us to a final provocative thought to consider, based on what this source has shown us.
Okay.
Given the distribution patterns discussed, concentrated in these specific, well-defined high-risk zones, and knowing that these forces are driven by the fundamental, ongoing movements deep within the Earth movements that will continue for millennia, what does that imply for the human societies that have settled and built their lives within these very active regions?
That's a big question. How do we live with this?
Right. How might future volcanic eruptions or seismic events driven by these same continuous processes specifically impact these populations and their infrastructure? And what does the persistent reality of living in these powerful, dynamic landscapes truly mean for how we plan, how we build, and ultimately how we coexist with our active planet?
It's a geological reality with profound human consequences, isn't it? Something really important to think about.